Well, welcome back after your relaxing weekend. I hope you've recovered from your midterms a little bit. Or you have more midterms? Not relaxing. Okay. Oh, dear. Well, a couple of comments about the progress of the course. Now, there are different parts, right? I give the lectures, and I show you some demos, and I try to explain the concept as best that I can, kind of fill in and add to what's in the text. The text, as I said at the beginning, is, I think, very succinct, very brief. It says everything that you really need to know in very few words and very well organized. I add some more things to it, like, for example, you learned about ferroelectricity here. You didn't find that in the text. And there'll be other things as we go along, of course, that I'll add. And also I subtract things that I think you don't necessarily need. Like, for example, there was a whole chapter on alternating current circuits. And all we took out of that was transformers. Because the rest is a little bit too detailed, I think, from my point of view. So we left that out. But so this part goes on in the lecture, and part goes on in discussions and labs. Now, if you're not getting what you need from those two parts, please respond. You see, the truth of the matter is, it's a funny relation we have with students. On the one hand, we work for you, right? I mean, you pay tuition or however you got here, and we work for you. So we have to satisfy your needs. On the other hand, we grade you. So it's a kind of funny thing. There's different levels of power here. But you have power. And the point is, I would like you to, if you're not getting what you need, please insist on it. Like, for example, if my lectures are not clear enough, good enough, whatever, talk to me. I'm here to listen. Or if in the discussion groups they're doing things that you don't get or it's not really what you need, talk to the GSI. He's going to be responsive. He doesn't know exactly what you're getting or not getting. So don't be afraid. Just go ahead and talk to us and insist on getting what you want. If, for example, there's too much math in the discussion sections, there isn't much math here, right? I mean, I don't work out numerical examples very much. A couple of times I did it, but not much, because I'm busy with all these things here and trying to explain things, so it's not convenient. I have to give up something else, which I hope is pretty unique from my point of view. On the other hand, if the discussion part is not providing you with what you need, like maybe connection between the lecture and the problems and so on, and you want more explanation there, tell it to your GSI, look, I want a better explanation. Don't be afraid to. There's only a group of 20 of you in the class. The chances are if you have problems piecing these things together, somebody else does too. So I'm just telling you now, we're only about, well, better than close to halfway through the course. There's plenty of time to make what I like to call a mid-course correction, and we can do things better, but with your feedback, okay? So don't be afraid to do that, and it's in your interests and ours, too, because we want to deliver a good job to you. On that score, any questions or anything else questions? Okay. I wanted to pick up a couple of points from the last lecture, which was on Maxwell's equations. And you recall that the key thing that Maxwell did was to modify Ampere's law for how you get magnetic field. Ampere was able to say, if I have a current, I can get the magnetic field around that. The magnetic field, it turns out, comes in loops around the current. And the magnetic field is given by, if you make a right-hand rule, this would be, you go around in this direction. This would be a negative current, so if the current was positive, it would be B going around this loop would be the current. So you have a loop around here, which tells you the current inside multiplied by this mu zero factor. Okay, so what Maxwell did was say, well, there's something else that could produce a thing where there is no current. And if you just have an electric field that is changing in time, that also, or actually it's the electric flux, will also act as a current. This is just as good a current as actual charges moving through a wire, or even charges just without even a wire, just free charges represent a current. So this is an additional current, displacement current, which adds to this equation. So instead of just mu 0 I, you would have mu 0 current of charges, real charges, plus this epsilon naught d phi electric dt. So just think of it as an additional current that adds to the genuine current, the real physical massive current, and is able to create a magnetic field. And the point is that even in empty space, you can have a varying electric field because electric fields go out into space. And they can actually create magnetic fields. And from this addition, he was able to predict the existence of waves of electricity and magnetism. So that was Maxwell's contribution. And we talked about various properties of the electromagnetic waves. The one that I didn't do too completely was, well, I don't have a demo to show you, for example. I had one demo which was interesting, and that was that I had a generator which sent out electromagnetic waves and excited an antenna. So we had a generator here, and it has its antenna, and it sent electrons up and down its antenna, which sent electric field out. See, for example, it could send electrons up here. There's an electric field that, say, goes to minus here and sends out an electric influence, which drove the electrons in synchrony, well, slightly delayed because it takes time for the electric field to arrive here. It travels at the speed of light from here to there. Didn't take much time in our classroom here. But there is a delay, and the electrons are driven up and down that antenna, and actually they lighted a little light bulb that was here because you could deliver energy to this. Now, I'll do a little numerical problem for you. Can we estimate what the frequency of this oscillator was just from our recollection of what we did? We had an antenna that was about, I think it was about this long, recall? So that's roughly, it turns out that the antenna, and this is a general kind of thing, the thing that interacts best with a wave is if the length of the thing is roughly the order of the wavelength. If the length of this thing is roughly the order of the wavelength, it interacts pretty strongly. It's again this idea that if there is a length in the problem, it probably interacts with the wavelength best. Just a general rule of thumb. So from this, can we tell what let's see if we can figure out what was the frequency of that oscillator. Anybody have an idea how to go about that? Do you remember we just brushed over quick, so maybe it's worth doing. That the velocity of a wave is equal to its frequency times its wavelength. That's a very important rule. Okay? So let's just make a ballpark estimate. If the length is that about a meter, roughly? About a yard? Yeah, it's about a meter, I would say. So the length, in our case here, was about a meter. Ballpark. Okay. So so we're going to say that the wavelength is roughly the same length as the antenna. So that's 1 meter. Now, what's the velocity of the wave that was coming out? Velocity of light, which is 3 times 10 to the 8th meters per second. Okay, so that's the velocity. So here we have this equation. So let's solve for the frequency. The frequency is then 3 times 10 to the 8th meters per second over the wavelength, or the L here, 1 meter length. So the meters cancel, and the frequency will come out 3 times 10 to the 8th per second. Per second is sometimes written in honor of a famous physicist. Frequency in per second is called hertz, after Heinrich Hertz, who was the first person to actually verify that man could make radio waves in the lab. He actually had a spark thing where he sparked electric pulse, and he had a little capacitor or a little gap over here, and the electric wave was so strong that it sent a wave and caused a spark over here. So he actually transmitted an electric wave from one place to another in the lab, which was the first time that ever been done. In any case, so hertz is the per second. So we have here 3 times 10 to the 8th. Hertz, if you like. Okay, so what is that? That's in that's a megacycle. A megahertz is 1,000,000 hertz. Mega million. So this is like 300 megahertz. It's a little higher than it actually is because the antenna is this is only a ballpark estimate, within a factor of 10. So this is how you would use this kind of equation. And this is an important piece of information, how the wavelength of this. So 300 million hertz. Now, by the way, you may not have ever noticed this, but radios, you have a radio, it'll have an AM band, and it'll have an FM band. Did you ever notice, if you look at it, it'll sometimes say kilohertz, and sometimes this will say megahertz. So those are the frequencies that the radio can pick up. It turns out that the AM radio, you get numbers like 670, numbers like 600 kilohertz. Yeah, so that's the frequency at which the AM stations are broadcasting, 600, 700, 800, 1,000 kilohertz. That's thousands of hertz. So it's much less. It's 1,000 times less than the FM bands, because they run, like I know a station, sort of like 90 megahertz. This is KQED, for example. My famous KQED is around 90 megahertz, 90 million cycles. That's a much higher frequency. The FM bands. Someday maybe we'll go into what is the difference between AM and FM radio. Does anybody know about that? It's nice to know. Oh, I'm getting distracted again. I should plunge on to this. But these are the frequencies that have been assigned to radio, AM radio, and FM radio. One is in the megahertz range, sort of like this antenna that we have. In fact, the antennas on the Sutro Tower are probably about that long also, that are broadcasting to us, FM. And then the towers that are broadcasting AM, if you go down to the bay, you'll see these tall buildings, tall towers. I think I showed a picture once of that. They have to be, because they're in the kilohertz range, their wavelength is much longer, and the antennas again, have to be much longer. So you have these tall towers for AM radio, and you have a TV also is sort of in the megahertz range, and the wavelengths are about like that. TV and FM are typically about like that. It's good to know. I don't know why it's good to know, but it's good to know somehow. But now the issue of polarization is that comes about, polarization comes about because it's an electric wave. And this is what Maxwell predicted and has been confirmed brilliantly. And that is that this electric, the wave that's coming out has an electric component and at right angles to it, a magnetic component. And the direction of propagation is in the direction of E cross B. So this direction of C is E cross B, as it happens. And the interesting thing is that you can get, each bit of light has an electric part polarized linearly, usually, like this. Now, when that strikes an antenna, that electric field being polarized that way, if the antenna is parallel to that, it drives electrons up and down the antenna. And that's what we did with that experiment that I showed over here, or before, the one up here. When the antennas were parallel, the way I drew it here, we got a nice fat signal picked up here. On the other hand, if I had my generator this way, and I put the antenna perpendicular to it, the electric field is driving this way, the antenna is this way, it really doesn't pick up anything. So you get no absorption in the antenna in this condition. And that's because of the polarization of the electric wave that's coming out, because I'm driving it this way, so I'm getting an electric field going from plus to minus, and it drives the current in here. So there is this polarization effect, and if the electric field is parallel to the way the current can flow, you get good absorption in the antenna, so you get energy delivered to the antenna, and that's enough actually to light up this little bulb. In the case when the antennas are crossed like that, this guy is radiating, but there's no place for the current to go. So there's no absorption in this antenna this way, nor this way. It doesn't radiate in this direction. The idea is that what you get radiation when you can see the acceleration. If the charges are going this way, you can see the acceleration, right? But if they're going this way, you don't see the acceleration nearly as well. So you don't get any radiation endwise. So this will radiate. Well, somehow the acceleration. Do you see acceleration when I go like this? Very much? Not very. If you have very good depth perception, you do. But it's much stronger this way. So in fact, there is. It actually comes out of somehow the dipole thing, because your field is kind of a dipole, and there's sort of nothing going in that direction. But there is quite a lot coming sideways. So these linear antennae radiate sideways and nothing endwise. And we showed that because I actually brought this antenna over here, and it picked up nothing. Even though it was parallel, it picked up nothing because this guy's not radiating in that direction. See here, he's radiating in this direction, but if he's oriented wrong, you don't get any absorption in the antenna. Okay, so the same principles are working in Polaroid materials, which I think you're going to work with in the lab, and that's why I did want to mention it quickly. Namely, let's see. So we have here a polarizer where by the way, the direction in which the Polaroid passes is if the electric field gets through, we say that's the direction of polarization, because the Polaroid is letting the light get through. So we say the light that comes through is this way. The light that was going this way is absorbed. So we can say this is the direction of polarization because the light gets through. Now, we've marked these. Oh, this one here. So, for example, we were doing this after class last time. It's kind of fun. So now you see me. And if I put the thing with the light from me, that you're seeing me, is polarized. Once it's cut through this, it's polarized in this direction by this Polaroid. If I put a similar Polaroid with the same direction, you can sort of still see me, more or less. But that's good or bad, I don't know, but here it is. You can see me, and I can see you too. But, see, the light here coming from me is polarized in this direction. If I put the Polaroid the other way, it doesn't pass through. I can't see you, and you can't see me. On the other hand, now we see each other again. Because the light from me is polarized. Once it goes through the polarizer, it's polarized this way, the direction of polarization. It'll get through this one because this one's polarized the same way. So it's going this way and it'll come out. On the other hand, this one only lets light through this way, but there's no light this way because it's this way. So that's, now you see it, now you don't. Pardon me? Yeah, no, it doesn't matter. That's a very good point, because I'm about to, yes, ma'am. I'm about to show you where it does matter how you do it in a way. Yes, ma'am. Yeah. So look, the light coming, that's a very good point. The light coming from me, we're going into this, is reflected light from the lamps. If there were no lamps, it would be dark, and you wouldn't see anything. There'd be no light. Okay, but that light is totally unpolarized. It's in every which direction, and when it hits me, it bounces off, and that's what you see. And we're going to make the point that we really see by reflected light most of the time. It's not an interesting point. The reason we see light is because we have some artificial light, like the lamps, the sun, but we ourselves don't emit light. All we do is we see each other in reflection. Okay, so the light is reflected off me, but it's coming in all different directions, bunch of individual waves, but every which way. Okay, so that's any individual wave, but there are zillions of individual waves in all different directions. What this thing does, it only lets through those waves that are vibrating this way, electric field vibrating this way, or some component of it. If the wave were vibrating this way, this component would get through. The cosine of the angle, that's one of the laws. Cosine of the electric field gets through. This one has no cosine of it, doesn't get through. So this one is absorbed. All that comes through is this. Think about it. Okay. It's a little tricky point, maybe. I don't know. But going back to his point, it's an interesting point. So there is this thing here is a polarizer, and its direction is this way. And if I put this here, the light, I'm putting them in line, so the light goes through as we showed before. Now I'm going to cross them, and now it's crossed to the one that was here, right? So now it's dark. So that's what I just showed you also. But now suppose I take another one and I put it in here, and I even turn it. I'm putting it above the first one. This is going to get to your point of, does it matter which one comes first? If you have two, it doesn't. But if you have three, it does. It's crazy. Now, so there was no change regardless of which direction I have here. Now suppose I put it here. You see it lightening up? What's that cancel? Well, what it's doing, it's a trick. It's a trick. Let's do it again, maybe with a little more visibility. Here, no matter where I put it, doesn't look like it's changing anything. So it's crossed and it stays crossed. Here, you see how it gets brighter? You will see that? So it doesn't matter where I put this thing. That's an interesting point. And it's a funny point, but it's actually pretty easy to explain, I think. It's semi-unbelievable, actually. And the argument is, see, if I had them, first I had something like this, crossed, right? And nothing came through because what came through this was blocked by this. Okay, now if I put the third one up here, no matter what it does, it's going to let some light through any old which way. Even if it has a component in this direction, that component will get through, but only the component parallel to this will get through. And that will be stopped by this one. On the other hand, what is an amusing thing that happens, if I put the polarizer between them and they're crossed, if I put this at some angle in between, there is a component, see, this one comes through. Let me try to draw it. This one comes through this way. I've got the polarizer at some angle. There is a component of this along this. See, this has components this way and that way, say. I can compose this of this. So this has a component parallel to this one. So some light actually goes through in this peculiar direction, and that has a component in this one. So some component does get through when the light is in, because the intermediate one is able to sort of turn the direction of the light that passes through. So the light started out this way, but it picks up a component that way. Or you think about that. That is an interesting thing. So the order does matter if you have three or more. This is a good point. I don't know if it's made in the book or not. Okay, so, but the thing is that there are actually, see this dipole radiation coming out. This is an important point, that the radiation of an electric dipole that goes out sideways and not upwards, and that has many consequences. And we demonstrated it a few times, and here it is again. The order is important. And so we have these polarized waves. The direction that the electric field gets through, we call the direction of polarization. That's the light that comes through. Unpolarized light has all these different directions. That's what's coming out of the lamps. And when you pass it through a polarizer, you see you started out with... You started out with unpolarized light, and only the component that was parallel to the passing direction will go through. Now, this diagram is actually poor, because he shows the wires, and since the wires going up and down, that's actually wrong. In order for it to get through, the wires would have to be that way. That's another thing we saw the other day, right? So this, I don't know where I got that diagram, but I should not have used it. Now, so there is a polarizing direction, the direction in which the electric field gets through. And the component, if the electric field happens not to be exactly along that direction, it's the cosine of that one electric field that gets through. And by our law that energy is proportional to the square of the field, we say that the energy that gets through goes as the cosine squared of that. See, it goes as cosine squared because the E field is going as the cosine and the energy is going as the square. So that's so-called Malous's law. Okay, let me stop that and go on to a whole other subject, namely, if you have questions, please raise them to me or to the GSIs. You'll be doing something in lab about that. Oh my, what happened? Did I lose that? I lost it. Let me try again. I'm going to do reflection and refraction here. Okay. Now here, what we're doing is we're going into simple optics, where what's called ray or geometrical optics, where we've said up till now that a light is a wave. If the wavelength is very short, which it is in the case of light, you can sort of forget about the wavelength for the time being and just consider the direction in which the light will propagate. So we speak of the ray of light, and we don't really worry about the fact that it's a fluctuating wave. Now, this is the outline. These are the important points. There's a principle called Huygens principle, which helps explain how things work. And we're going to talk about reflection and refraction. This is going to be the subject of your lab this week. Here's the point I made just a little bit earlier, that we actually mostly see by reflected light. And there's two things. But basically, it's really the law of reflection. Sometimes it looks a little different because you can have a rough surface, and rough surfaces look like they're not reflecting, but they are. The point is that we have the law of reflection. Namely, you have a surface, light will come in and will reflect off. And the law of reflection is that the angle in which it's incident, theta, if you will, theta 1, compared to the angle in which it's reflected are equal. That's the law of reflection. Now, I think that is true of everything. So we give this, but if you have a mirror where this is actually observed, we call that specular, or, obviously reflective thing like a mirror. On the other hand, if you have a rough surface, the law of reflection actually is working at every point. The problem is that there are different angles that the light is striking a rough surface. And so the light scatters in all directions. So we call that diffuse, but really what it is accumulation of specular things. The example I would give you is if you take a shower. Before you take the shower, you look in the bathroom mirror and you see yourself in the mirror. If the room steams up and the mirror steams up, you don't see yourself. You more or less see the mirror. That's the difference. The mirror is going to give you a specular reflection. Once it's fogged up, the light is reflecting off the fog that's accumulated, and you sort of see the mirror. You don't see you anymore. You see the light coming on from everywhere, including you, is hitting the foggy mirror, but it's scattering in all directions. You don't see a real image of yourself. So that's the diffuse reflection. Now, we'll do some demos here of what you're going to be doing similar things in the lab. Let me try to turn off some of the lights, maybe. This is a can you see these light beams here, way back yonder? Wow, you got good eyes. Okay, then that makes life easier because I don't have to switch elements around. So what we're demonstrating here is several things. The first is the law of reflection. Here's a light coming in. It's striking this surface, partially reflected. You see that beam here, right? And you'll notice that the normal to that surface is about here. And the angle with respect to the normal, we measure angles with respect to the normal, is the same as the angle of reflection. That's the law of reflection. Now, the other thing that you see is that compared to the normal here, obviously this beam inside the material is bent. If you again do the normal, the angle to the normal is less here. Do you agree with that? You see, you want to measure with respect to the normal. The angle here is less than the angle here. So what I'm seeing is, let me try to draw the picture. We come in to the surface. Here's the normal. And the light is coming in here, and it's bending toward. So if this is an angle, this is the angle of reflection. This is the angle of incidence called, or theta 1, incidence, if you will. And this beam, this ray, is called the angle of the refracted light, and this would be the angle of refraction. And the way I see it, the angle of refraction is less. It bends toward the normal. You bend the light toward the normal. Now the reason for that is that the light is now passing through the medium. The speed of light, we'll say, is less in a solid medium or material medium. It could be water too. It could be, but it's a material medium. This is fairly generally true. There are some rare exceptions where the seemingly the velocity of light could be greater, but let's take it. So the point is, and that's by a factor which we call n, which is the index of refraction. So it tells you that the actual velocity is equal to the velocity of light over this parameter n. And n is typically a number like 2, 3, 5, something like that. I think water is 3 or something like this. So we show that. Here's the law of reflection, and it is explained by both of these phenomena. Both reflection and refraction can be explained by a single principle called Huygens' principle. Huygens was actually a contemporary of Isaac Newton and was a very brilliant physicist. In fact, he competed with Newton because Newton thought that light was particles, because he said, look, if I look at the shadow of an edge, it looks pretty sharp. So it must be that there's particles here. And Huygens had the opposite point of view, was that light was a wave. But a wave would diffract. A wave does funny things. For example, if you have a wave coming into a pillar and a pier, say, you'll find that the wave appears a little bit behind the pillar. But particles will be shadowed perfectly. So Huygens said, well, these are waves, and Newton said, no, they're particles. They're both right, as it happens, but they act as both ways, actually, as we'll see in modern terms. But Huygens, by his thinking of waves, he said how a wave propagates is by, so we make a distinction between a wave-like phenomenon, and we speak of the wave fronts, that is, sort of the crests of the waves. So these are the wave fronts. That's a term you want to understand. And then there's the ray of the wave, which is the direction in which the front is progressing. So we have two ways of looking at a wave. We can look at the crests moving, and there's a line of crests moving, or we can just take one ray and say that's the direction in which the fronts are moving. So we have those two ideas to describe the motion. And Huygens said, well, the way a wave moves is that every point on the wave sends out another little wavelet. And the wavelets superimpose and give you a new front. It's a cute idea. And it turns out to be pretty close to our modern thinking, because the way light might travel through a material like that is that it strikes the surface, and it's an electric field, and there are atoms here. So that electric field grabs onto the electrons and starts shaking them, makes them into little antennas, makes them into little oscillators. Or more like an antenna. It's not an oscillator. They're driven. You're driving the atoms up and down with the electric field, and they re-radiate. So in a way, Huygens guessed right, actually. And so each point on the wave radiates its own little wavelet. We call them wavelets. And the wavelets progress. So by that means, by Huygens' thinking, we can derive the law of reflection, for example. I don't think I have time to go through all the bloody details of this, but you can just think of a wave coming in, wave fronts, and then think that once the wave strikes this reflecting surface, it re-emits a wave going back out. And then if you actually calculate the direction in which the wavelets add up, you'll find in the case of reflection that the angle out, reflected, is equal to the angle of incidence, just by the Huygens construction. Now, in the case of the refracted wave, if you have a wave coming in, it's going at a velocity c in air, roughly c. But you see, once it hits this material, this part of the wave slows down. So because it's in the medium here and it's driving little oscillators, it's driving the atoms, and the speed is slower, so that whereas a wave, if this was a wave front arriving here, the wave front, let's see, what you'd want to say is, a very important point I should make, and that is that when a light hits a medium, the frequency is the same. The frequency is the same in both media. That's a very important point and should be physically obvious, because what's happening, the electric field is coming in and it's shaking things, right? It's moving along. Now, it doesn't shake any less frequently when it's inside the medium. It's still shaking, but it's just going slower. So what changes here is the wavelength. once the wave goes in here, the wavelength changes. The wavelength, again, is equal to the wave speed, v, over the frequency. Right. So if the velocity goes down, the velocity is c over n. That's the speed in the medium. I'm thinking here. Times the frequency. Now the frequency stays the same. The speed of light is what it is. So the wavelength is made less by the wavelength. Then will go inversely as this refractive index. So what happens is if you have a refractive index more than 1, the wavelength is going to be less. It's going to be the original wavelength over n. Keep making bad ends. Sorry about that. I will come to a bad end, I'm afraid. So there you go. So what happens is that the light comes in, slows down, keeps going at the same frequency of oscillation, but the wave doesn't advance so fast, so the wavelength gets shorter in the medium. You might think of it as like a soldier's walking. When you're walking, you walk into mud, your steps get a little bit shorter, you can't progress as fast, and people get a little bit closer. In other words, that's a good analogy. Suppose you had a row of soldiers, and they step into mud. The guys in front going a little slower, you catch up to them, so your wavelength, the distance between you, gets shorter, because you're all marching to the same beat, but you can't go. You're going slower, so you catch up. So the wavelength gets shorter. That's a very important physical point. So that's pretty much it. I have derivations which you can look at. They're actually in my PowerPoints here, where you can see from the Huygens point of view these wavelets coming out, these little bubbles of radiation, and you can prove that the waves that add up will be those where the angle of incidence is equal to the angle of reflection. Then we have diffuse reflection, that is of all different things. And again, the frequency is constant, but the speed changes, meaning that the wavelength gets shorter in the medium. See in this picture here, once the wavelengths are pretty far apart. Once it hits the medium, the wavelengths shorten up, the speed slows down, but the frequency, you can't show frequency here, it's time, stays the same. And that's very important. And here is a collection of various indices of refraction. For liquids, it's about 1. For glass, it's about 1.5. Your eyeglasses, for example. And diamond is pretty high. And some materials are fairly high. But you don't get too gigantic thing. But, the point I would make that these are measured at one particular frequency. And we're going to see later on how this can vary with frequency, and that can be an important fact. One thing, do we have any time? No. Maybe 1 minute. Let me show you, again, a couple of interesting phenomena. This is what I want to do. I want to see. Look at this ray here, going here. Now, here now is the light is going from a dense medium. See, because this curved surface is going in along a radius, it's going from a dense medium to a less dense medium, and going into the less dense medium, it bends away from the normal. It's sort of the inverse of what we had before. See, also these things are reversible, such that if a light comes in at a big angle, it'll refract at a small angle. But look what happens if I tilt. See how that ray is getting closer and closer to the surface, and pretty soon it can't get out. This ray, here it is here. That's this ray coming through. See, it's this one. and it's coming out. But if I make the angle big enough, it can't get out. It's what's called total internal reflection. Total internal reflection. That light is totally trapped inside. That's one phenomenon you're going to work with. This is very important. Actually, the fiber cables that carry light signals, TV and stuff like that, they use total internal reflection. They don't want the light to get out of that wire, glass fiber. It reflects in and out. The other phenomenon that I wanted to show you, if you have a minute more, and by the way, those of you who want to go to, there's a wonderful lecture, I think it's going to be good at iHouse, if you can get to it. The phenomenon I wanted to show was when, if you can see, I'm trying to get the light reflected to be perpendicular to the light refracted. I don't know if you can see this one, but there's a beam over here. Can you see that? And it's at right angles to this. When that's at right angles, it's polarized, such that, this is awful. One direction doesn't get through. I don't know if you can see this. You'd probably have to be up close. The point is, when this is a phenomenon where when the reflected beam is at right angles to the refracted beam, this beam becomes polarized. This also can be understood. Yes, sir? The reflected beam is polarized. The so-called Brewster angle, or the angle of polarization. If you shine unpolarized light on a surface, and you can get the key thing is that this ray has to be perpendicular to the refracted beam. So you have what we have here is two phenomena of 90-degree angles, which are different but similar in some respects. The one is total internal reflection, where if you go from a dense medium, and when the angle of refraction is 90 degrees, that's total internal reflection. You have here a 90-degree angle. The other phenomenon is another 90-degree, but different. You come in with a beam of light. The reflected beam is this way, and the refracted beam is that way. If you can get that angle to be 90 degrees, this beam will be, there will be no polarization this way. It will only have polarization in that direction. This will be yes, polarized, and no, polarized. This can be understood because this is an antenna. These are little transmitter antennas radiating, and it doesn't radiate in this direction. So there is no polarization in this